According to conventional wisdom, the universe was said to have started with a tremendous explosion that created space, time, and everything in it. However, there are some who believe that this story may be incorrect and that the Big Bang actually occurred after something far stranger. These scientists contend that we are not merely existing in the universe, but rather we are being swallowed by a cosmic monster, a black hole so massive that it spit out our reality. If this is so, then what does it imply for our perception of reality and what happens when we die? We're in a black hole. Does that imply everything we've ever known is wrong? Black holes are among the most mysterious phenomena in the cosmos, and their immense gravity isn't the only thing that makes them intriguing. They also cast doubt on our very conception of reality. The history of black holes is as fascinating as the phenomena itself, with many unexpected turns along the way. What gives planets their significance is the way they captivate our imaginations and shape our perception of the universe. The concept of black holes originated in the 18th century with the work of British clergyman and scientist John Michell, who hypothesized that certain stars could be so dense that their gravity could trap light. While Michell did not use the term black hole to describe these objects, his theories established a foundation for subsequent scientific investigations. These ideas remained largely untested for nearly 2 centuries before they were revived as legitimate scientific concepts in the early 20th century. However, everything changed when Albert Einstein proposed his theory of general relativity. Rather than seeing gravity as a force, Einstein portrayed it as the bending of space-time. This new way of thinking allowed for the possibility of black holes to be considered. Schwarzschild discovered something astounding while solving Einstein's equations in 1916. Under certain conditions, a star could collapse into a point so dense it would create a gravitational sinkhole, now known as a black hole. Schwarzschild's discovery was monumental, but it was overshadowed by World War I. Einstein himself found it hard to believe that such extreme structures could exist, but mathematics doesn't care about preferences. Schwarzschild's work provided a fresh perspective on the cosmos. He not only proved that black holes existed, but also defined their boundaries, now referred to as event horizons, beyond which nothing, not even light, could escape. Despite this, many scientists still questioned whether or not black holes actually existed in the actual universe, and Einstein persisted in casting doubt on this possibility. Opposed the idea, claiming that they were blatant misinterpretations of his work. It wasn't until astronomers began to uncover signs of otherworldly objects in the universe that black holes were finally accepted as real. The discovery of Cygnus X1 in the 1960s shifted everything, as it was a binary system in which one star appeared to orbit nothing but nothing. The scientific community finally accepted it as a black hole, which only added to its fascination. Some scientists believe that black holes may hold the answers to some of the universe's greatest mysteries due to the warping of space and time. This isn't just a theory, though. It has been observed in regions with extreme gravity that clocks tick more slowly. So, if you were to hover near a black hole and look back at Earth, time would appear to be moving faster here than there. Even before scientists could prove their existence, poets and writers were already conjuring images of black holes in their works. In Edgar Allan Poe's poem Eureka, for example, the universe is collapsing in on itself, a concept that echoes the contemporary idea of a singularity and was influenced by Einstein's work. Surrealist painters like Salvador Dali incorporated ideas of the infinite into their work in the 20th century, and black holes became popular. Physicist John Arthur Wheeler first used the term black hole in 1967. Prior to that, the objects were known as frozen stars or dark stars. The new name stuck, in part, because it conveyed the air of mystery around the objects. But even as black holes became commonplace, the science behind them remained shrouded in mystery, as seen in films like Interstellar and Disney's The Black Hole. As matter spirals towards a black hole, it forms an accretion disk, which is filled with gas and debris. When the disks get hot enough, they emit intense X-rays that astronomers on Earth can detect. Black holes also release jets, which are energy streams that escape at nearly the speed of light. The process behind this is incredibly complex and elusive, which can extend thousands of light years, impact both the evolution of galaxies and the distribution of matter throughout the universe. Scientists place a high value on black holes because of the role they play in shaping their surroundings. Cosmic giants, such as the Sagittarius, a star at the center of our galaxy, can be millions or even billions of times heavier than ours. In contrast to the Sun, black holes occupy a space slightly smaller than our solar system. Their gravitational pull connects entire galaxies, making it impossible to imagine a universe without them. While some cultures view black holes as symbols of destruction, others, like Hinduism, see them as symbols of creation and destruction in an endless cycle. Interestingly, some interpretations of these myths align with modern scientific theories. The dance of Shiva represents creation and, like black holes, which devour and redistribute matter. Indigenous myths also mention cosmic voids or devourers of light, implying that humanity has long struggled with the concept of things beyond comprehension. But black holes are intriguing for more than just their cultural connotations. They also push the limits of what science can teach us. At the center of a black hole, where density is infinite, is one of the biggest mysteries in the universe. Some physicists believe that the Big Bang, which started the universe as we know it from an extremely dense point, was a singularity. The interconnections between black holes and other cosmic events are far more intriguing, and the most brilliant lights in the sky could be the result of such a singularity. Our present knowledge of the principles of physics fails us in this case, and the concepts of space and time become meaningless. The most powerful objects in the universe, known as quasars, are powered by incredibly massive black holes. Scientists and the general public are fascinated by these paradoxical entities, which can both create and destroy. New technology has allowed us to get a closer look at black holes, and the Event Horizon Telescope, part of a worldwide network of observatories, captured the first ever image of one in 2019, astronomers captured a picture of galaxy M87's supermassive black hole, which was a cultural as well as scientific milestone. The image showed the black hole's shadow encircled by its bright secretion disk, confirming many predictions from general relativity. However, the discovery also prompted new questions. What lies beyond the shadow? Could these regions contain clues about the universe's hidden dimensions? The possibility that our universe might actually be inside a black hole isn't as implausible as it once seemed. According to some scientists, black holes in higher dimensions could potentially house multiple universes. This theory is connected to the holographic principle, which states that our perception of three dimensions could be a projection from a two-dimensional surface. In this perspective, black holes aren't merely cosmic oddities. They're portals to comprehending reality's essential structure. The relationship between black holes and the structure of the universe has been further strengthened through the study of gravitational waves. Since their first detection in 2015, scientists have been able to listen to the cosmos through waves in space-time that are often the result of black hole collisions. Each new detection adds to the growing body of evidence demonstrating the mysterious and interdependent character of black holes and the universe as a whole. While many questions remain unanswered, black holes are crucial to comprehending the universe's beginnings, from the formation of galaxies to the theoretical foundations of black hole theory. Albert Einstein's theory of general relativity fundamentally altered our understanding of space, time, and gravity. Previously, people believed that gravity was a force acting between two objects, such as the Earth and the Moon. Einstein argued that this was incorrect and that gravity is actually just a representation of the distance between objects. Space-time curves, caused by massive objects like planets and stars, bend space-time, causing smaller objects to roll toward the larger object. This new theory of gravity wasn't merely theoretical. It explained many things about the universe and, most intriguingly, predicted the existence of black holes, which weren't immediately apparent. Accepted as real entities when Einstein released his equations in 1915, even he had doubts about their existence, because the ideas seemed too strange. However, Carl Schwarzschild solved these equations for the first time under extreme conditions in 1916. His solution demonstrated that a massive star could collapse under its own gravity and form a point of infinite density, a singularity around this point. The groundbreaking work of Schwarzschild was overshadowed by the chaos of World War I. He worked on his equations while serving in the German army and didn't live to see their full impact. Nevertheless, his discovery laid the foundation for what we now know as black holes. The event horizon is a key feature of black holes. It is not a physical surface like the ground we walk on. Anything crossing this boundary would be lost forever and unable to turn. Instead, it's a mathematical boundary if you approach it with enough speed, that is faster than light, than what is required to escape gravity inside the event horizon. Beyond this point, the laws of physics as we know them become illogical because time and space are so distorted that they are practically useless. At the black hole's core, there's the singularity, where density becomes infinite and the curvature of. There are various sizes and types of black holes. Stellar black holes, formed when massive stars collapse at the end of their life cycle, are usually several times the mass of our Sun. Additionally, there are other types of black holes that are hidden from the outside world by the event horizon, which prevents us from directly observing them. Some scientists even question the existence of singularities altogether. Intermediate black holes are smaller than stellar black holes, but larger than supermassive ones. These are harder to detect and are believed to form when smaller black holes merge. Lastly, there are primordial black holes, which, if they exist, formed in the early universe. Supermassive black holes, which are millions or even billions of times more massive than the Sun, reside at the centers of most galaxies, including our own Milky Way. One such supermassive black hole is called Sagittarius A star. Black holes, both large and small, have the potential to shed light on the nature of dark matter, the enigmatic substance responsible for the vast majority of the universe's mass. As they spin, certain black holes like the Kerr black hole drag spacetime around with them, a phenomenon known as frame dragging. Another type of black hole is the electric-charged Reiner-Nordstrom black hole, which may or may not actually exist. The electrical neutrality of most space objects makes charged black holes very unlikely to exist in the actual universe. One of the most interesting things about black holes is the energy they emit. Even though nothing can escape their event horizon, a gaseous and dusty ring called an accretion disk is formed as material falls into a black hole. When the contents of the disk reach temperatures in the millions of degrees, they release radiation that are planets. X-rays and other radiations may be absorbed by Earth's atmosphere, and some black holes release powerful energy jets that send particles hurtling out into space at nearly the speed of light. These jets shape stars and galaxies, and they can be thousands of light years long. Near a black hole, time appears to stand still compared to farther away. This phenomenon, called time dilation, is not just theoretical. Experiments conducted on Earth have shown results that are quite similar. The study of black holes has also helped us understand other cosmic phenomena, such as quasars, which are powered by supermassive black holes at the centers of galaxies. These black holes cause the apparent slowing of time as their gravitational fields become stronger. Hovering just outside the event horizon, you would be able to watch the universe accelerate around you. Observations of gravitational waves, which are ripples in space-time caused by the collision of massive objects, have provided direct evidence of black hole mergers. These waves were first detected in 2015 by the Litchfield Observatory and have since been observed in numerous other instances. Quasars are a striking example of how black holes, which are often thought of as destroyers, can actually be sources of immense energy. Black holes aren't entirely black. They gradually lose energy as virtual particles form near the event horizon. This shrinkage causes the black hole to become smaller and smaller, and each detection not only confirms Einstein's predictions, but also helps scientists learn more about the universe's most extreme events, Hawking radiation. This concept was proposed by Stephen Hawking and adds another layer of complexity to black holes. Hawking radiation has not been directly observed yet, but it has profound implications for our understanding of black holes and the laws of physics. Some scientists even think that black holes could be linked to other parts of the universe through wormholes, which are theoretical tunnels that link different points in space-time. While these ideas are still purely theoretical, they raise intriguing possibilities about reality and the structure of the cosmos, such as the holographic principle. As a result, I'm intrigued by them. From their formation to their role in shaping galaxies, black holes are essential to understanding the universe. They challenge our understanding of physics and push the boundaries of what we know about space and time, whether through their immense size or the possibility that everything inside a black hole is encoded on its event horizon. New ways of thinking about information entropy and the universe at large have been inspired by this idea. Whether it's their gravitational pull, their capacity to bend light, or their enigmatic singularities, black holes never fail to captivate both scientists and the general public. One of the most intriguing theories put forth by the string theory is the possibility that our universe contains more dimensions than the 3 we currently know. According to this theory, there could be as many as 10 or 11 dimensions, but they're so tiny and twisted that we can't perceive them in our everyday lives. Dimensions that do not consist of length, width, or height, but rather exist on a different scale. These hidden dimensions are crucial to string theory. Without them, the math does not hold when discussing a universe inside a black hole. One such model is brane cosmology, which derives from string theory. According to this theory, our universe is like a brane floating in a higher dimensional space, sometimes referred to as the bulk. We're like a sheet within this larger space and other. We may be surrounded by branes. Black holes could be connections between branes or portals to other dimensions. One possible explanation for the perceived weakness of gravity compared to forces like electromagnetism or nuclear forces is that part of it escapes our brane and into the bulk. This theory also suggests that black holes could be objects in a higher dimension. From this vantage point, they might appear different. In our three-dimensional universe, black holes are tiny, dense dots encircled by event horizons. However, in higher dimensions, these objects may take on more complex shapes, such as spheres, and their properties may undergo changes. Some theories even propose that black holes in higher dimensions could create new things by stealing bits of space-time, which could result in the birth of a new universe. M-theory, an upgraded version of string theory, expands on these ideas by stating that, too. If we want to make sense of the cosmos, we'll have to deal with 11 dimensions. According to M-theory, black holes are more than just points in space. They're potentially multi-dimensional objects called black branes. These black branes could have an impact on not only our universe, but on other dimensions as well. Some scientists even speculate that our universe may have originated from a black hole. In a higher dimension, a black hole could collapse, leaving behind the Big Bang and the black hole universe hypothesis. This theory proposes that the conditions inside a black hole could be similar to the Big Bang, with all the matter and energy condensed to the point where space and time collapse. Some scientists even go so far as to say that this tremendous compression could spur the creation of a new universe with its own set of rules and structure, with the event horizon serving as a boundary between. Similar to how our own universe has no visibility beyond its boundaries, the event horizon separates various worlds. Some observations from our own universe suggest this possibility. For example, when scientists examine the cosmic microwave background, a faint glow from the early universe, they find patterns that are difficult to explain. Some of these scientists have speculated that these patterns could be the aftermath of a black hole's collapse, which would explain how our universe formed. Existing within a black hole could provide light on the mystery of our universe's invisibility, much like the event horizon obscures what's inside a black hole. Another key piece of this puzzle is the holographic principle, which proposes that the three-dimensional reality we perceive is actually encoded on a two-dimensional surface. This concept initially arose from research into black holes, where researchers discovered that data regarding objects falling into a black hole appears to be stored on. Black holes aren't merely cosmic vacuums. According to this theory, They're actually information storage devices that encode details about their parent universes. The strange relationship between black holes and the universe goes even further. Some scientists think black holes could explain the universe's faster expansion, which would explain the existence of dark energy, the mysterious force responsible for this. If our universe is contained within a black hole, then its expansion could be caused by external forces. This would mean that the accelerated expansion we observe is not solely due to our universe's characteristics, but rather is a consequence of its connection to a larger structure. The black hole hypothesis is related to the laws of thermodynamics, particularly the second law, which states that entropy or disorder always increases. Black holes also possess entropy. This discovery has surprised scientists because it suggests a connection between black holes and space-time. It also relates to the holographic principle, which states that all information is contained in an object's surface area rather than its volume. If our universe is contained within a black hole, its entropy could be stored on a two-dimensional boundary, offering a new way of looking at reality structure. Additionally, time acts strangely in a black hole as objects approach its event horizon, slows down in comparison to an outside observer. This phenomenon, known as time dilation, may explain why the expansion of our universe seems to be speeding up from inside a black hole. This theory is related to the black hole universe hypothesis, which states that the flow of time inside a black hole differs from the flow of time outside it. These ideas are not limited to black holes in our universe. They could also apply to black holes in other universes if they exist in M. In theory and brain cosmology, black holes have the potential to impact not one, but several universes or dimensions. They could serve as connecting points between various parts of the multiverse. Some researchers go so far as to suggest that black holes could even give rise to new universes or baby universes, which would be smaller regions of space-time that split off from the main universe. This process of branching would make black holes similar to cosmic seeds, where new universes are grown within them. Quantum gravity is also crucial to the ongoing effort to reconcile quantum mechanics with general relativity. Using black holes as examples, some theories of quantum gravity propose that these objects contain quantum seeds that, given the correct circumstances, could sprout into new universes. These seeds, in turn, could contain the blueprint for how a universe could evolve. For example, the conditions on the Planck scale near a black hole singularity, the region of maximum density and smallest scales, could be similar to those at the beginning of our own universe, lending credence to the idea that black holes generate new realities. Black hole thermodynamics, which studies black holes' temperatures and entropies, also gives hints that the entropy of a black hole scales with the area of the event horizon rather than its volume, suggesting that the structure of space-time could be closely related to dark energy, which comprises most of the universe's energy. This exchange would expand our universe from the inside out. This view challenges the traditional Big Bang theory as a one-time event, proposing instead that our universe could be one of many created in a multiverse filled with black holes. The ideas linking black holes to other universes may sound complex, but they create an intriguing picture of how the universe might work. Black holes are suggested to be more than just points of infinite gravity. They're key elements in a much larger cosmic structure. Though it may sound fantastical, the idea of parallel worlds actually originates in quantum physics, which states that particles can exist in more than one state simultaneously. Some researchers are now considering the possibility that black holes could be created if we had the power to shape reality itself. For example, instead of turning right, we could turn left. On the other hand, we could decide not to have lunch. When these subtle variations are replicated across an infinite number of possible outcomes, we would have a massive multiverse. Black holes could be the key to unlocking these parallel universes, according to one theory. According to this theory, each universe is like a bubble in an endless foam of universes. Each bubble forms when a new universe pops into existence, and each bubble has its own set of fundamental constants and laws of physics. On the one hand, these bubbles could exist independently of ours. On the other, Black holes could connect these bubbles through their intense gravitational pull, allowing energy, matter, or even by allowing information to flow between them. Black holes serve as portals that link what were previously believed to be separate realms. According to another theory of the multiverse called the brain theory, our universe is actually just a single three-dimensional brain floating in a higher dimensional space called the bulk. If black holes exist on these brains, they could form invisible connections between them, allowing information to travel between them. It's possible that energy or gravity is leaking from one brain to another through black holes, which could explain why our universe's gravity seems so weak. However, there's another theory that some scientists propose. The singularity inside a black hole could be linked to a white hole in another universe. In this theory, the white hole would be the polar opposite of a black hole, pushing matter in rather than pulling it out. If this connection is true, then the matter would be forever lost. If this is true, then whatever goes into a black hole in our universe could come out in a different form in another. We can't see this connection from outside the black hole, but it could mean that black holes aren't simply cosmic dead ends. They could be points of exchange where universes interact in ways we don't fully understand. Wormholes, which are often thought of as space shortcuts, could play a role here as well. Some researchers even think black holes might stabilize wormholes, creating bridges that aren't. The energy required to maintain these wormholes open would be enormous, potentially emanating from the black hole's rotation. Wormholes might not connect 2 points in our universe, but rather connect various universes, creating a network where black holes serve as hubs for transport between realities. In order to stabilize a wormhole, scientists believe that exotic matter, which contains negative energy, is necessary. It does not exist in our everyday reality, but in theory it could hold a wormhole that could allow us to travel through it. Some physicists believe that black holes, on a microscopic scale, may contain smaller wormholes that connect to other universes. On a quantum level, these wormholes could represent an unseen web that links not only galaxies but entire universes. If black holes could connect universes, it would change our conception of reality. Instead of living in a single, closed universe, we might actually be part of a vast network. In a model where all universes are interconnected and black holes serve as cosmic portals, ours isn't an isolated ball in space. Rather, it's a cog in a vast cosmic wheel. This theory raises some interesting questions about the nature of space and time, such as whether or not there's a real edge to our universe. Alternatively, if black holes are portals, each one could lead to a different realm, and they could even recycle matter and energy from other universes, making them more than just endpoints. They would be cosmic recycling centers, transforming matter in one universe into another. If black holes could transport energy between universes, this would explain some of the mysteries in our own, such as dark energy's acceleration of expansion. Some scientists speculate that forces from other universes could be subtly pushing everything outward through black holes, adding another layer to the black hole theory. In conventional physics, data is never really lost. However, when an object falls into a black hole, it appears as though all associated information is erased. This has scientists wondering if black holes are portals through which data can be transported to other universes, where it could be preserved in a different form. In this scenario, what we perceive as loss could actually be the passage of a threshold that we haven't fully comprehended in relation to relativity and quantum mechanics. When two black holes merge, they send out gravitational waves that ripple through space-time and travel across the universe. Some scientists believe these waves might carry signals from other universes, leaving faint echoes that we could one day detect. Quantum entanglement, in which particles stay connected even over enormous distances, could also imply a hidden connection between black holes in different universes. Someday, we may be able to tell if this is correct, and if so, every black hole merger could shed light on the structure of the multiverse. Other clues include patterns in the cosmic microwave background, a faint radiation remnant from the early universe, that scientists find puzzling. Some speculate that these patterns may be evidence of interactions between universes perhaps facilitated by black holes. Lastly, there are gamma bursts, which are extremely powerful bursts of energy that appear to originate from faraway galaxies. Their origins are a mystery to many scientists, who have speculated that they could be signals from other universes' high-energy black holes or even Hawking radiation, which could reveal information about other realms. If black hole radiation patterns don't match our expectations, it could indicate that something strange is happening, such as energy leaking from another universe. By studying these discrepancies, we could learn more about the cosmos beyond our own. Black holes have long been believed to be impenetrable barriers that could only allow matter to flow in one direction. However, some scientists have speculated that certain black holes could actually allow energy to travel in both directions, creating a bridge that could allow the flow of both matter and information. If black holes are indeed portals, then what happens to objects that cross the event horizon? Are they destroyed or reassembled in another universe? The concept of black holes as entrances to alternate realities is more than just a pipe dream. It's a way of perceiving the cosmos that questions our current understanding and prompts us to speculate about what could be beyond. If black holes are, in fact, gateways, then they may conceal the details of a multiverse that is larger and more complex than anything we've ever imagined. Every black hole could serve as a portal, leading to a hidden reality that is simultaneously real and infinitesimally distant, beyond the influence of Einstein's field equations. While Einstein may not have anticipated their future relevance, the 10 internal differential equations that link mass, energy, and the curvature of space-time are fundamental to our understanding of black holes. These equations do more than provide numerical values. They also describe the twisting, bending, and stretching that takes place under the intense gravitational pull. According to the equations, space-time can compress into an infinitely dense point under specific circumstances. This phenomenon is known as a black hole. Carl Schwarzschild was the first to find an answer to these equations for a non-rotating, perfectly spherical black hole. His solution, the Schwarzschild solution, describes the event horizon and predicts the behavior of light and matter around it. However, in practice, black holes are rarely so simple. They rotate, interact, and collide with one another. For rotating black holes, computational assistance is typically necessary due to the complexity of the solutions needed. The Kerr solution adds another layer to the problem by explaining how a black hole's spin distorts space-time, causing a cosmic whirlpool where space itself twists. This effect, called frame dragging, is so strong that it warps everything surrounding the black hole, including light. Because the equations describing this rotation are so complex, scientists typically use computers to run simulations that. The process of simulating black holes involves more than just plugging numbers into a computer. By breaking down each black hole into smaller and smaller pieces, like a grid over space-time, scientists can determine the gravitational pull on each point. They update the positions of these points every fraction of a second using numerical relativity, which relies on computers to handle the massive calculations required to keep up with Einstein's equations in real time. While dealing with complex phenomena like black holes, researchers can use techniques like finite difference to break down the differential equations into smaller, more manageable steps. By monitoring the change in space-time at each step, they can piece together a picture of the black hole's behavior over time. Another important method is adaptive mesh refinement, which boosts precision without overwhelming the system. Simulations of black hole mergers must take into consideration the enormous gravitational forces at work. When two black holes collide, it's a violent event that sends shock waves through space-time, similar to the waves on a pond. The simulations must follow the spiraling motion of the black holes as they approach each other, emitting gravitational waves that ripple through space-time. After the merger, there's a ring-down phase when space-time vibrates and eventually settles. Black hole mergers are not just a theory. Patterns in gravitational waves match predictions from simulations, proving that these models are correct. The theory was brought to life in 2015 by Virgo and LIGO's observations of merging black holes. With each new detection, our understanding of black hole behavior is refined, including the kick or recoil that results from these mergers. The process of simulating black holes, which involves moving them away from their original positions and then watching them interact with one another, is a laborious and time-consuming endeavor. However, the results are worth it because supercomputers like Blue Waters and Summit can perform billions of calculations per second, allowing scientists to recreate black hole dynamics. Some simulations can run for weeks or even months, and scientists use parallel processing to divide the calculations across hundreds or thousands of processes. The mysterious nature of black holes has long fascinated astronomers, who have used simulations to gain insight into their inner workings. One such effect is the peculiar behavior of light as it approaches these massive objects. Geodesic tracing, a method that follows the path of light around a black hole, allows scientists to model how photons loop and twist in the black hole's gravity. The end result is a photon ring, a brilliant circle around the black hole where light loops multiple times before either escaping or being pulled in. The Event Horizon Telescope, EHT, confirmed what simulations had predicted, that the ring in the image of the M87 black hole appears to be bent around the black hole's gravity through the use of interferometry, which combines data from telescopes all over the world. This creates a global network with a resolution high enough to image black hole shadows. Advanced algorithms then recreate the black hole from the processed data. Full-field pictures of black holes allow us to see the shadows cast by the event horizon. This visual data agrees with simulation predictions, which aids in the verification of models with real observations. However, simulations don't merely stop at imaging. They also disclose other insights, such as how black holes create Acker disks, which are whirling rings of gas and dust that heat up to millions of degrees as they approach the black hole. Simulations show that these disks are extremely turbulent, with particles colliding at high speeds. This is supported by the data. The X-rays emitted by these collisions can be seen by astronomers using space telescopes, providing a glimpse into the harsh environment surrounding black holes. Additionally, computer simulations reveal that these objects can unleash powerful particle jets that can travel nearly at the speed of light, originating from their poles. Supermassive black holes spin their magnetic fields, causing them to release particles in massive streams called jets. These jets can extend for thousands of light years, resembling a star formation, and maybe even galaxies in general. The mathematics underlying these simulations poses special difficulties, especially close to the singularity, where density becomes infinite. Regular computations fail at this point. To circumvent these issues, scientists employ techniques such as excision, in which they relocate the singularity from the grid. This allows simulations to concentrate on the event horizon and the surrounding areas, where the majority of observable effects take place, and coordinate transformations, which helps simplify the math by altering them. When scientists change the standard grid layout to one that better fits the shape of a black hole, their simulations run more smoothly and accurately, giving them a better picture of the black hole's behavior. The dynamics inside a black hole reveal strange effects, like the warping of the event horizon, and simulations show that black hole events use spherical and polar coordinates, which make calculations more manageable. Black holes bend light and matter nearby in unique ways as they spin, creating frame-dragging effects that twist space-time around them. This effect, predicted by relativity and confirmed through simulations, is especially pronounced in fast-spinning black holes. As a result, horizons aren't perfectly smooth and can form bulges or twists, particularly in black hole mergers. Cosmic whirlpool surrounding the black hole. These models have also shown that when two black holes merge, they create distinct gravitational wave signatures, or tones, similar to those on a musical instrument. The specific frequencies of these signatures, known as quasi-normal modes, are dependent on the mass and spin of the black hole, so scientists can infer these characteristics from the data collected by measuring gravitational waves. With each new development, such as in the study of gravitational wave signatures, frame-dragging effects, or photon rings, we get closer to comprehending black holes as more than just sins. They are complex dynamical entities that follow patterns predicted by math and confirmed by simulations, causing a distinct kind of turbulence in the accretion disk and allowing us to detect and study X-rays. Mathematical models and simulations that help us understand the most extreme environments in the universe. Einstein's field equations, which may sound abstract, are fundamental to our understanding of black holes. These equations do more than just provide numerical values. They also describe the complex interplay between mass, energy, and the curvature of space-time. When Einstein published them in 1915, he likely did not envision their implications for the future. Today, these equations are essential for comprehending black holes, and their complexity is becoming clearer as scientists apply them to these objects. Under specific circumstances, the equations state that space-time can compress into a singularity with infinite density, giving rise to the black hole we know today. The first solution to these equations, called the Schwarzschild solution, was found by Carl Schwarz for a non-rotating, perfectly spherical black hole. This solution defines the event horizon and predicts. Real black holes are rarely this simple. They spin, interact, and collide, necessitating more complicated solutions and, in most cases, computational assistance for spinning black holes. The Kerr solution adds another layer. It explains how a black hole's spin distorts space-time, creating a cosmic whirlpool where space itself twists. This effect, called frame dragging, is so powerful that it warps everything around the black hole, including light and the equations. In order to simulate the intricacies of black hole dynamics, scientists utilize computers to run simulations. However, simulating a black hole is more involved than simply plugging numbers into a computer. By breaking the black hole into smaller components, such as a grid over space-time, scientists are able to calculate the gravitational pull on each point in the grid, taking into account nearby points and updating their positions fractionally every second. This method is known as numerical relativity. To keep up with Einstein's equations in real time, computers handle the massive calculations. One method, adaptive mesh refinement, focuses computing power on critical areas like the event horizon. This technique increases accuracy without overloading the system, which is essential when dealing with black hole behavior. Another method, finite difference, breaks down the differential equations into small, manageable steps across the grid. Each step calculates changes in spacetime. Simulators of black hole mergers must take into consideration the enormous gravitational forces at work in these events. When two black holes collide, it's a violent event on a cosmic scale. As they draw near, they release gravitational waves that ripple through spacetime like waves on a pond. The simulations must follow the black hole's intricate spiraling paths as they merge. And afterward, there's a ring-down phase when spacetime vibrates. Slowly but surely, it settles into a steady state, emitting specific frequencies known as quasi-normal modes. Scientists are able to detect these modes using instruments like Virgo and LGO. The patterns in gravitational waves match the predictions from the models, proving that the theories are correct. The theory was brought to life in 2015 by LIGO's observations of merging black holes. And with each new detection, our understanding of black hole behavior is further refined. This includes phenomena like the recoil or kick, which occurs when a black hole is pushed away from its. Extensive simulations of black hole dynamics take weeks or months to complete, utilizing parallel processing to divide calculations across hundreds or thousands of processes. Despite the time, energy, and patience required, the results provide valuable insights into the interactions of these massive objects. Supercomputers, such as Blue Waters and Summit, are capable of handling billions of calculations per second. Giving us a peek into the inner workings of these cosmic behemoths, simulations help us make sense of the peculiar effects that black holes have on light. One such technique is geodesic tracing, which mimics the path that light takes around a black hole. This allows scientists to model the way photons bend and loop due to the gravitational pull of the black hole, creating a bright ring around the black hole where light loops multiple times before either escaping or being pulled in. The Event Horizon Telescope, EHD, confirmed what simulations had predicted. That light bending around the M87 black hole is the cause of the ring in the image. The EHD uses interferometry, a technique that combines data from telescopes all over the world to create a global network with a resolution high enough to image black hole shadows. The data is then processed using advanced algorithms to recreate black hole images. Scientists are able to confirm their models with real observations thanks to simulations that show us shadows see by the event horizon. But simulations don't stop at imaging. They also reveal other insights, such as how black holes create accretion disks, which are whirling rings of gas and dust that get hotter as they approach the black hole, reaching millions of degrees. The simulations also show that these disks are very turbulent, with particles colliding at high speeds, and that the energy from these. Astronomers are able to gain insight into the intense environment surrounding black holes through the X-rays emitted by collisions, which can be detected by space telescopes. Simulations have also shown that supermassive black holes are capable of releasing powerful jets of particles that shoot out from their poles at nearly the speed of light. These jets originate from magnetic fields that are twisted by the black hole's spin, releasing particles in massive streams. These jets can extend for thousands of light years, impacting star formation and even shaping entire galaxies. Galaxies, the mathematics underlying these simulations poses special difficulties, especially close to the singularity, where density becomes infinite. Regular computations fail at this point. To circumvent this, scientists employ techniques like excision, in which the singularity is removed from the grid. This allows the simulations to concentrate on the event horizon and the surrounding regions, where the majority of observable effects take place, and coordinate transformations, which alter the way distances and directions are. As a result of these adjustments, simulations of black holes run more smoothly and accurately, bringing us closer to a realistic picture of their behavior. The dynamics inside a black hole reveal strange effects, like the warping of the event horizon, and scientists can model them using coordinates that make calculations more manageable. Spherical and polar coordinates are common choices because they align better with a black hole's shape than standard grid layouts. Intense gravitational interactions, such as those that occur in black hole mergers, can distort horizons, causing them to bulge or twist. This, in turn, bends the light and matter in the vicinity of the black hole in surprising ways. As black holes spin, they produce frame-dragging effects, which twist space-time around them. This effect, predicted by relativity and confirmed by simulations, is particularly noticeable in rapidly spinning black holes. These frame-dragging zones draw material from nearby, creating the cosmic whirlpool surrounding the black hole is just one example of how these models have shown that merging black holes leave behind unique gravitational wave fingerprints, much like an instrument's tone. By analyzing these fingerprints, scientists can potentially determine the mass and spin of a black hole. This is because the frequencies involved, called quasi-normal modes, are dependent on the mass and spin of the black hole. Each of these advancements, whether in gravitational wave signatures, frame-dragging effects, or photon rings, brings us closer to understanding black holes as more than just cosmic neutron stars. They're complex dynamic entities with intricate patterns that influence the movement of neighboring particles. As a result, the matter in the accretion disk, heated to millions of degrees, emits X-rays, which we can detect and study, validating our modeling predictions. Mathematical predictions and simulations have given us models that can help us understand the most extreme environments in the universe, such as black holes. When you cross a black hole's event horizon, you enter a realm where gravity doesn't work. Once you cross that boundary, you're pulled inexorably toward the center, toward the singularity. There's no turning back. Gravity is a constant. Regardless of your power, there's no getting out of this area. Time starts to distort and changes as you approach the event horizon, making you appear slower and your image fading. This is caused by gravitational redshift, a phenomenon where intense gravity causes light waves to be stretched to longer, redder wavelengths, which eventually become invisible to the observer. It's not just a poetic term. In this strange landscape, there's an effect called spaghettification. It means that, due to the intense difference in gravitational pull between your head and feet, you would be stretched long and thin like a piece of spaghetti. In smaller black holes, this stretching happens before you even reach the event horizon. However, in supermassive black holes, with less mass, it happens after you've already passed the event horizon. Extreme tidal forces near the boundary could potentially cause you to cross the event horizon relatively unscathed. However, once you're deeper inside, the pull becomes stronger and the effects on space and time become even more extreme. Some theories even propose that space and time swap inside a black hole. So as you fall inward, moving forward in time actually brings you closer to the singularity. In other words, it becomes your inevitable outcome. Time itself is pulling you inexorably closer and closer to the black hole's singularity, the point at which all our knowledge of the universe becomes obsolete as density approaches infinity and conventional physics breaks down. At this point, some scientists speculate that quantum effects could alter the outcome, creating a Planck star instead of an infinitely dense point. However, no one knows for sure. When our current understanding of reality comes to a halt, it may be time to reevaluate our theories. One extreme possibility is that black holes contain baby universes, which would be distinct regions of space-time that would branch out from the parent universe. According to this model, matter that gets pulled into a black hole could eventually form a new universe, existing in a different space but linked through the black hole. This idea may sound far-fetched, but it is mathematically feasible that such an unreachable universe could exist within a black hole. From the outside, everything follows its own unique schedule and set of physical laws. Some theories, like the wormhole theory, propose that black holes could link other universes or even different regions of our own. The math supports the idea that such connections could exist, but how to safely traverse them is another question. In response, some scientists have proposed a firewall, a high-energy barrier that destroys matter as it passes the event horizon, to prevent anything from entering black holes. Arriving at the singularity intact inside a spinning black hole could be an even stranger experience than expected. Instead of a single point, the singularity could take the shape of a ring, changing the black hole structure. This ring-shaped singularity would create an area where the usual rules of physics, such as cause and effect, would no longer apply, and the future would be filled with uncertainty. This would leave us wondering what happens to. The problem of data retention also arises from classical physics, which states that anything that falls into a black hole is permanently erased. However, quantum entanglement has the potential to link particles near the event horizon with particles outside, suggesting links that extend beyond the boundaries of black holes. This connection means that an object's loss to the black hole could still have effects on particles far beyond the black hole, creating a cosmic bridge that science is only beginning to investigate. This theoretical disagreement gave rise to the now famous black hole information paradox, which proposes that all the information within a 3D region of space could actually be encoded on its 2D surface, almost like a hologram. The idea arose from an earlier discussion about the holographic principle and the edge of reality, which dragged information inexorably toward the singularity and then lost forever. Jacob Bekenstein, a physicist, made a groundbreaking discovery in the 1970s when he realized that a black hole's entropy, a measure of disorder or information, was proportional to its surface area. This went against the intuition that information should be stored within a volume, not on a surface. Instead, the amount of information a black hole can contain depends on the area of its event horizon. Gerard Ta, a physicist, first noticed this strange connection in the 1970s. The holographic principle, developed by Leonard Susskind, postulates that, in a sense, reality may just be a detailed projection from information stored on a distant 2D boundary, similar to a cosmic hologram. If black holes store information on their surfaces, then maybe our entire universe functions in this way. This principle has profound implications for our understanding of reality. The holographic principle suggests that space and time may be emergent rather than fundamental, which could be a bridge between quantum mechanics and general relativity, two branches of physics that describe different realms. General relativity governs massive gravitational environments, while quantum mechanics governs the tiny subatomic world. This could explain why quantum mechanics and general relativity clash in extreme environments like black holes. One of the most intriguing parts of the holographic principle is its ability to resolve the black hole information paradox. This paradox arises because, according to quantum mechanics, information cannot be lost. However, what happens to something that falls into a black hole and is swallowed by the singularity? The holographic principle suggests that this information might not vanish, but instead be encoded on the event horizon and preserved in some form. Even though it appears to be lost within the black hole, another important piece of this puzzle is the anti-deep conformal field theory, also known as the CFT correspondence. This concept was developed by physicist Juan Malacha, and CFT demonstrates that a theory of gravity in one dimension can be described by a theory without gravity on a boundary in another dimension. This idea lends credence to the holographic principle by offering a mathematical model for how a three-dimensional space could be completely described using data on a two-dimensional surface. Some have utilized this model to claim that if the holographic principle is valid for black holes, then the entire universe could be a projection of our three-dimensional reality. We couldn't see anything in the physical world directly, and everything we perceive as real could actually be encoded on a distant surface, calling into question our most fundamental assumptions about the nature of reality. Some have even speculated that dark matter exists outside of black holes. Experimental evidence supporting the holographic principle is indirect, but intriguing observations of black holes could provide light on the mysterious force driving the accelerated expansion of the universe. While this theory is still in its early stages, it adds an intriguing dimension to our understanding of cosmic expansion and raises the possibility that interactions with the holographic boundary could influence the universe's energy. In experiments conducted at CERN and other particle physics labs, scientists are driving particles to near-light speeds, exploring the boundaries of what might be considered traditional spacetime, and the resulting shadows cast by black holes demonstrate how light bends close to these objects. These advancements in particle physics have hinted at behaviors that could be compatible with the holographic perspective. In addition to the questions it raises regarding our perception of reality, the holographic principle raises the question of whether our awareness is limited to what is projected onto an unseen surface, or if our perception is a thin slice of something larger encoded on the edges of our perception. This theory challenges not only our knowledge, but also our understanding of the world around us, touching on both physics and philosophy. A new perspective on the data loss process within a black hole is offered by the holographic concept, which suggests that all the information and particles contained within a black hole might be imprinted on its 2D boundary. This idea does more than just reshape black hole theory. It forces us to rethink the universe and our place in it. Questions about existence, perception, and the nature of reality itself are also raised by this idea. Although general relativity provides a framework for understanding black holes in the context of massive objects subjected to intense gravity, quantum mechanics takes over at the microscopic level, revealing that particles within these objects do not behave in a conventional sense. This leads to some perplexing contradictions when trying to combine the two frameworks within a black hole, one of the most. This black hole information paradox has been around for a while, but it all starts with a simple rule in quantum mechanics. Information cannot be destroyed. In classical physics, anything that crosses the event horizon seems to vanish, pulled toward the singularity. However, in quantum mechanics, losing information breaks fundamental rules. Stephen Hawking's discovery of the complexities of Hawking radiation in the 1970s were further amplified by the fact that it is a result of quantum fluctuations close to the event horizon, wherein a pair of particles momentarily appears, with one particle falling into the black hole while the other gradually escapes. As a result, the black hole loses mass and shrinks until it evaporates. But here's the catch. If the black hole disappears, Where does the information it swallowed go? Does it vanish along with the black hole, or does it remain in some other form? So far, numerous theories have been put forth in an effort to decipher this information paradox. One of these is the holographic principle, which states that a black hole's internal data could be stored on its two-dimensional surface. If this is indeed the case, then any data that enters a black hole would be encoded as information on its surface, where it would remain intact even after the black hole evaporates. Two of the physicists responsible for this concept have since revolutionized our understanding of black holes. Another theory, known as black hole complementarity, proposes that information could exist in two places, inside the black hole and on the event horizon. From an outside observer's perspective, this information would remain on the surface, but for an object hurtling towards the black hole, it would remain inside. This idea creates a kind of dual reality that doesn't violate quantum rules, and quantum entanglement could provide a solution. As far-fetched theories go, there's the firewall hypothesis, which proposes that data remains accessible through an invisible connection to the outside world, even if particles fall into a black hole. This theory involves two particles becoming entangled, with the relative positions of the particles becoming irrelevant to how changes to one particle influence the other. According to this theory, an energy wall forms at the very edge of the event horizon. This is supposed to prevent scientists from having to account for data contained inside the black hole. However, this theory contradicts certain fundamental physical laws and has not gained much traction so far. Instead, scientists have turned to theories like loop quantum gravity, which proposes that space and time are made up of tiny loops, not continuous structures, creating a quantum core inside black holes instead of a singularity. This core could prevent matter from collapsing completely and preserve information without violating quantum rules. Another model, the fuzzball theory from string theory, suggests that black holes might actually be composed of tangled strings instead of a singularity, storing information within their structure. However, testing these theories is challenging because black holes are Black holes are too far away and too shielded by their event horizons for scientists to peer inside them directly. Nevertheless, they can learn about the properties of black holes through the gravitational waves that ripple through space-time when two of them merge. Hawking radiation is another obstacle. It's a slow process. The radiation a black hole emits is very faint, and for large black holes, it's impossible to study gravitational waves because they carry information about the properties of the black holes themselves. Einstein's theory of relativity suggests that space inside black holes isn't smooth but filled with constant tiny changes. This structure would mean that particles can't reach infinite density, potentially. Detecting Hawking radiation is beyond our current technology, but scientists are working on alternative ways to explore the effects it predicts at the smallest scales. Space-time may be foamy, filled with tiny fluctuations that affect the behavior of particles and forces. Loop quantum gravity also introduces the concept of a Planck star, a dense core inside black holes where matter reaches maximum compression without collapsing into a singularity instead of an infinite density. The Planck star represents a stable state within quantum limits. If this model is correct, it would imply that black holes contain fluctuating foam-like structures that prevent the formation of a true singularity. This could help explain how information is stored and could even hint at a quantum structure of space-time itself. Information is contained in a compact form instead of being lost in an unreachable point. Some theories even go so far as to propose that just before they reach infinite density, particles on the brink of the black hole singularity undergo a rebound effect, which would prevent complete collapse, preserve information, and keep the black hole's gravitational pull intact. This is all theoretical, but it does hint at possibilities that could one day alter our understanding of the deepest regions of the universe. Various theories have been put forth to address the black hole information paradox. These include entangled particles, loop quantum gravity firewalls, fuzzballs, and the possibility that particles inside a black hole could still be connected to particles outside. This connection could enable information to leak out of the black hole in subtle ways while maintaining the link with the outside universe. However, none of these theories have offered a comprehensive solution. No one knows for sure what happens to matter, energy, and information in a black hole's intense gravitational field, but scientists are re-evaluating the rules of physics in an effort to piece together these mysteries. As we delve deeper into these mysteries, it's becoming apparent that black holes are more than just sinks for gravity. They're windows into the nature of reality, offering clues about cosmic inflation and the origins of black holes, as well as other cosmic phenomena. According to cosmic inflation, our universe, which was once much smaller than an atom, expanded at an unprecedented rate of expansion in the tiny fraction of a second. Alan Guth initially put this theory forward in 1980 to explain the universe's seemingly flat and smooth appearance. This rapid expansion, or inflation, would stretch space itself, eliminating any irregularities and giving the impression that the universe is uniform when viewed from a large scale. The question then becomes, why would anything expand at such a rapid rate, and why did it cease allowing the universe to? The theory of cosmic inflation explains why the universe is expanding at a much slower rate after a certain point. It also helps with what physicists refer to as the horizon problem. Without inflation, faraway parts of the cosmos wouldn't have had time to exchange light or heat, so they should appear very different. Instead, they look very similar in temperature, which suggests that they did interact in some way. Inclusive inflation provides a comprehensive explanation for the smoothness of the universe and sheds light on the formation of galaxies and other structures. During inflation, minute quantum fluctuations, essentially random changes of the smallest scales, were magnified into larger patterns, giving rise to galaxy clusters and the structure of the universe as we know it today. The cosmic microwave background, CMB, still contains faint remnants of these original patterns, lending credence to the idea. According to some scientists, our universe may have started as a black hole in a larger universe. This theory suggests that the Big Bang, which we perceive as a period of rapid inflation, may actually have been the formation of an event horizon. From an outside perspective, this could have resembled the growth of a black hole's event horizon as it drew in matter. This fits in with the holographic principle, which states that everything within the universe could be a projection from information encoded on its surface. It also aligns with the idea that the universe might function like an event horizon, containing all the information within. Some physicists are also considering the possibility that inflation is happening in other parts of the universe, which fits within this theory. According to the eternal inflation theory, which states that new bubble universes continue to form in specific locations, such as our own, even after inflation ends. These bubbles would expand during inflation, but they would each exist in their own space. According to this theory, each bubble universe could start with a black hole in a parent universe, and ours is just one of many. To understand how inflation could relate to black holes, physicists have examined the effects of matter and energy when they collide with these. As we draw near the singularity of a black hole, the enormous energy released by quantum fluctuations during inflation may mimic the conditions observed at the event horizon of a black hole, where space-time is stretched and bent. This resemblance has prompted some scientists to question whether black holes in our universe could create new universes within themselves, each beginning with its own type of inflation. Inflation also leaves behind evidence in the form of gravitational waves, which are ripples in space-time caused by massive cosmic events. These waves can be detected by instruments like the LIGO Space Telescope, suggest that the expansion of our universe could be a component of an inflationary phase, which would provide indirect evidence of inflation by revealing how space reacted to extreme events in the early universe. Detecting these waves is challenging, but every discovery brings us closer to understanding the forces that shaped our universe. Another theory, the Big Bounce, proposes that inflationary waves could help us understand how inflation works and whether they align with the black hole hypothesis. According to this model, The universe goes through an endless cycle of expansion and contraction before resuming its expansion in a new Big Bang-like event. Some scientists think that black holes could be involved in this cycle, with each contraction potentially creating a singularity that triggers an expansion. If this is the case, then black holes could be crucial not only to the beginning of our universe, but to subsequent cycles of creation as well. Moreover, comprehending inflation raises questions regarding quantum mechanics during inflation. Changes impacted every aspect of the cosmos. These changes may shed light on the quantum behavior of black holes and suggest that space-time contains quantum foam on extremely microscopic scales, wherein minute fluctuations continually alter and influence particles. This foam could even limit the formation of singularities, which would lower the density of matter within black holes. It could also provide clues as to what caused inflation. Some have speculated that it could have been stimulated by a quantum vacuum state, a situation in which extremely low energy levels allow for random fluctuations to cause abrupt and massive expansion. This idea has direct implications for black hole physics, as energy fluctuations close to an event horizon could cause similar stretching of spacetime. This finding raises the intriguing possibility that the same principles that explain inflation could also explain how black holes impact the space around them. Another intriguing perspective is the idea of a newborn universe developing within a black hole. According to this theory, matter and energy could undergo compression as they approach a black hole. Once inside, the conditions would be similar to the Big Bang. From this point of view, a new universe could form, expanding through inflation. Each black hole could serve as a cosmic seed, giving rise to universes with distinct properties and laws of physics. This has led some to speculate about the possibility of a multiverse, which would consist of an infinite number of universes, each with its own unique. It's a challenging question to determine what caused inflation to begin, since it's practically impossible to observe or reproduce inflationary conditions in a lab owing to the extremely high energy levels involved. However, if every black hole leads to a new universe, then our own universe could just be one branch in an endless network of realities. This concept pushes the boundaries of what we think is possible. Scientists are utilizing mathematical models and simulations to come up with ideas for what could cause black holes to expand so rapidly. Since we can't see into black holes, we can only speculate about what happens during inflation. Nevertheless, they're keeping their fingers crossed that by studying gravitational waves and the cosmic microwave background, they can uncover clues about the inflationary phase. Any new information could shed light on how our universe came to be, and perhaps even on the role black holes played in creating entire worlds. Inflation, which has its origins in quantum fluctuations and black hole dynamics, as well as the fast expansion of space, is still a mystery when it comes to the early universe. Suggestions about dark energy and dark matter have led some scientists to speculate that dark matter may actually consist of primordial black holes that formed in the early universe, rather than the usual black holes that form from collapsed stars. In the immediate aftermath of the Big Bang, these black holes would behave similarly to dark matter, exerting gravitational pull without emitting light. Their behavior is nearly identical to that of dark matter particles, adding to the mystique surrounding these two entities. Dark energy, along with dark matter, is one of the greatest mysteries of our universe. It accounts for approximately 95% of all matter, but remains unseen by humans. To keep galaxies from collapsing as they spin, dark matter is believed to consist of particles known as WIMPs that weakly interact massively. These particles have mass, which causes them to have an effect on gravity, but they don't interact with light or other particles in a detectable way. Experiments are being conducted all over the globe in the hopes of finding WIMPs, axion particles, which are so incredibly light that they behave more like waves than particles, could make up dark matter. These particles would bind galaxies together, creating an invisible fog. Another possible candidate for dark matter is the sterile neutrino, a particle that interacts solely with gravity. These particles could be floating around our universe unnoticed affecting the mass and structure of galaxies. Dark energy, which comprises approximately 68% of the universe, and explains why galaxies are receding from one another at an alarming rate. In contrast to gravity, which draws objects together, dark energy acts as a repulsive force, pushing galaxies apart. Some scientists have even speculated that dark matter could be emanating from dimensions beyond our own, influencing the universe in subtle but powerful ways. Distant supernova and discovered that galaxies were receding at accelerating rates, which could only be explained by a force like dark energy. However, some physicists believe that dark energy is not a material substance, but rather a property of space itself, similar to a constant background energy. This idea stems from Einstein's cosmological constant, a term in his equations that represents the fixed amount of energy in empty space. Additionally, there is debate regarding whether dark energy remains constant over time, or if it could change, possibly speeding up or slowing down at different rates. In the future, some theories suggest that dark energy could have its origins in another universe. This theory suggests that dark energy could be like a pressure from an external source pushing outward on our universe, coming from higher dimensional space through gravitational leakage from nearby universes. To understand this, imagine our universe as a three-dimensional brain suspended in a four-dimensional bulk. The force we call dark energy could be the result of influences from these other brains. It's possible that dark energy originates from interactions at the universe's edge, which could indicate a multiverse effect. If this is the case, it would imply that our universe isn't as isolated as previously believed and provide indirect evidence of extra dimensions. Additionally, black holes could increase their gravitational influence and create regions around them that resemble dark matter through interactions with quantum fields. If this is indeed the case, it could have significant implications. That the stuff we call dark matter could be nothing more than compressed matter from earlier cosmic cycles, held in place by invisible black holes. Another school of thought holds that dark energy and dark matter are really just two sides of the same coin, representing different aspects of an unseen force or particle that works in ways we don't yet comprehend. Take the modified Newtonian dynamics theory as an example. It implies that our current grasp of gravity could be lacking. On a grand scale, it undergoes changes that give the impression of dark matter, but it doesn't actually contain any unseen particles. Some speculate that dark energy is actually a byproduct of extremely energetic processes that occurred during the Big Bang, or perhaps the residual energy from black hole mergers or other powerful cosmic events that have spread out across the cosmos. If so, dark energy is a remnant of an earlier era of cosmic activity, perhaps connected to the initial stages of black hole formation. Could even stand in for invisible, parallel versions of matter and energy that we can't see or measure directly. This shadow matter could interact with our universe only via gravity, providing an unseen framework that supports and propels expansion. Scientists are looking into a variety of ways to identify dark matter, while dark energy detectors on Earth try to catch particles by observing their infrequent interactions with normal matter. So far, no definitive findings have been. Indirect evidence of dark matter can be found in observations of galaxy rotation curves. This is because galaxies spin at a rate that is greater than that which can be explained by visible matter alone. Dark energy effects can be measured through redshift, in which light from faraway galaxies shifts to longer wavelengths as space expands. There are further clues about dark matter in the afterglow of the Big Bang, where its gravitational influence affects temperature fluctuations across the universe. Mysteries like these raise serious concerns about the possibility that our cosmos is like a black hole. If dark energy is impacted by another universe, it could mean that our cosmos is expanding due to interactions with a wider space, and the structure of dark matter could suggest that our cosmos edge is expanding like an event horizon, with dark energy pushing outward like a black hole's boundary does as it consumes matter. Dark energy's consistent effects across vast distances are like the gravitational pull of a black hole's event horizon raises the possibility of a deeper connection, leading some scientists to suggest that black holes could be portals between universes. Dark matter and dark energy, they say, could provide clues to these connections. The way dark matter clusters around black holes suggests a possible connection to their origins, and the distribution of dark matter in galaxies is similar, suggesting that there may be a connection between the two. As black holes alter the fabric of space around them, advanced observatories like the James Webb Space Telescope may shed light on the nature of dark matter and dark energy by studying galaxies and supernova remnants at great distances. If primordial black holes are discovered to generate detectable space-time ripples, then improved gravitational wave detectors may provide further information regarding this mysterious substance. In a lab, scientists are attempting to recreate the conditions of the early universe in an effort to understand dark matter and dark energy. Shed light on the behavior of dark matter in large-scale interactions, where it seems to be less effective than regular matter. The nature of dark energy and the structure of our universe are still unknown, but new discoveries are revealing more and more about these invisible forces. As our understanding grows, we may be able to make sense of our cosmos, its relationship to black holes, higher dimensions, and possibly even other universes. The unseen forces at work in the universe, such as dark energy's push on the expansion of the universe and dark matter's creation of invisible structures to hold galaxies together. Black holes provide a direct boundary within which to study these mysteries. Of all the things about black holes, the most enigmatic is their event horizon, which acts as a barrier that not even light can escape. Due to the immense gravitational pull and the fact that there is no way out, black holes appear black from the outside. Despite this, scientists continue to study the event horizon in the hopes that it will shed light on what lies beyond. In 2019, the Event Horizon Telescope, EHD, finally succeeded in capturing an image of the supermassive black hole at the galactic center, M87, which revealed a glowing ring. EHD was able to capture a direct view of the event horizon of a black hole, which is visible as a bright ring around the black hole made of hot gas and particles that are spinning at almost the speed of light. The image is significant because it confirms predictions from Einstein's general relativity, which state that light bends around black holes, creating that distinctive ring as gravity warps the path of photons. Gravitational lensing, the extreme bending of light as it approaches an object's event horizon, is most noticeable in the vicinity of black holes, where the force of gravity distorts space itself. The Event Horizon Telescope, EHD, was able to record this phenomenon from such a distance because it pooled information from radio telescopes around the world, effectively doubling the size of Earth's telescope. Through this gigantic lens, we were able to make out details as minute as the 55 million light-year-away event horizon. The EHD images revealed even more intricate structures, going even deeper than before. Photon rings are layers in an image that form when light from a black hole has blasted around it several times before escaping. Each ring is slightly brighter than the others, representing the different degrees to which the black hole's gravity has bent the light. These rings show that there may be more than just an edge near the event horizon, and they lend credence to theories like the holographic principle, which states that as a hologram encodes a three-dimensional image on a two-dimensional surface, the contents of a black hole could be stored on its event horizon. This idea is related to the possibility that our universe has an event horizon where all the data pertaining to our reality is kept on a distant boundary. If black holes function in this manner, then our entire cosmos could be structured similarly, existing as a projection from this cosmic boundary. Black hole images also aid in investigating the idea that our universe might. The observable universe may function as an event horizon within a vaster cosmos, according to this theory. Just as light bends near black holes, the large-scale structure of space-time in the universe could potentially lens light, a phenomenon similar to what we observe around black holes, but on a cosmic scale. One intriguing finding of the EHD is the accretion disk, a ring of the dust and gas surrounding a black hole's event horizon forms a high-energy zone, which emits X-rays and radio waves. This zone is heated to millions of degrees as particles spiral inward. And by studying these emissions, scientists can learn more about black holes' feeding habits and how they affect their immediate environment. Nearby stars and gas are also affected by the high energy from accretion disks, which impacts the constellations and the formation of galaxies. Black holes aren't merely cosmic traps. They actively shape their surroundings, as shown by the recycling of matter and energy that occurs as matter spirals into them and breaks down under extreme conditions. Some particles are ejected in jets that shoot out from the black hole's poles at nearly the speed of light, while other particles are drawn into the event horizon. The Event Horizon Telescope has allowed for the detailed study of these high-energy jets by observing them. By studying the magnetic fields close to the event horizon, scientists can observe how black holes produce jets and how they impact interstellar space. These jets can carry particles and magnetic fields that interact with the surrounding galaxy, and they can even affect the rate of star formation. This highlights the central role of black holes in galactic ecosystems. As imaging techniques improve, scientists hope to monitor these jets in real time and study their evolution. Future upgrades to the Exploring the event horizon also allows scientists to test ideas about the information stored around black holes, since each photon ring in a black hole image contains light that has orbited the object. Adding space-based telescopes could further shed light on the finer details of black holes, allowing us to better understand how their sizes and spins affect their event horizons. With each new observation, we could learn more about black holes' interactions with their environments and their large-scale effects on the universe. Layers of photon rings around the black hole indicate that information about matter and energy that has gone into the black hole could be preserved in the light that orbits the event horizon, which could encode details about everything that has passed through it. Some researchers think the event horizon could serve as more than just a boundary. It could connect to other universes, according to multiverse theories. EHD's observations have brought us closer to understanding black holes, but they also raise questions about our universe. If black holes can store information on their event horizons, could our universe itself be a massive storage of information on a galactic scale? Additionally, observing how photon rings form and interact could provide clues to the largest structure in the multiverse. Cosmic boundary. This fits in with theories that say our world could be a hologram, a projection of data encoded on some faraway surface. Black hole images, with their complex photon rings and bending light, give us a look at how this could work, implying that what we see could be just a small portion of a much larger structure. Every new finding from the EHD adds to our understanding of black holes, which in turn hints at links to the universe's fundamental structure. Further information regarding the bending, storing, and manipulating of light and matter by black holes, which may provide light on the enigmas of dark matter and dark energy, as well as the likelihood that our cosmos operates similarly to the interior of a cosmic black hole. While black hole images allow us to probe the universe's hidden boundaries, the theory goes even farther by suggesting that our entire cosmos might be contained within a black hole, exist as the interior of a black hole in a vastly larger space, just as matter and light can escape from a black hole's event horizon. Supporters of this theory propose that our universe may also be bounded by a cosmic horizon, a limit beyond which we are unable to observe or reach. This theory draws striking similarities to the structure of black holes. For example, our universe also has a cosmic horizon, a boundary that restricts our view of the universe due to the fact that light can't traverse them. Our universe exhibits signs of space-time curvature on a grand scale, and space and time are distorted inside black holes due to intense gravity. Some argue that the Big Bang may not have been a singular starting point, but rather the instant a black hole formed in a higher dimension, lending credence to the idea that our universe might be an inner region of a much larger black hole structure. Here's a theory that could explain our universe's behavior. If we are actually inside a black hole, the rapid inflation of space right after the Big Bang could be a reflection of the event that happens inside a black hole as it draws in more matter. In other words, the inflation we see could be a reflection of the stretching effect around a black hole. This would explain why theories like quantum mechanics and general relativity often clash. But in a black hole, they both play a role. Important functions. Quantum mechanics explains the microscopic characteristics of particles, and the gravitational effects of relativity describe how black holes distort space and time. A universe shaped by black holes could bring together these two schools of thought, demonstrating that both influence our reality on different scales. However, beyond the event horizon of a black hole, space and time could switch places, meaning that time advances in the same way as space does, and everything is bound to eventually approach the singularity, according to some scientists. If this swap holds, then our universe could be encoded on a cosmic boundary, and our perception of reality could be a projection from this boundary. The holographic principle, which explains how time in our universe seems to flow forward toward what we perceive as the future, is in line with the black hole universe hypothesis. According to this principle, everything inside a black hole can be represented on its event horizon, like a 3D image encoded on a 2D surface. Scientists are looking at the cosmic microwave background, CMB, as a possible model that could explain the nature of the universe as a whole. The CMB shows us the early, hot universe, and its smoothness and uniformity could suggest that it began in a highly compressed state, like a black hole. Patterns in the CMB show how matter was distributed during this time, and studying these patterns could provide evidence that our universe may have originated inside a black hole. This theory's more theoretical aspects draw from brain cosmology and string theory. According to these models, our universe may actually be a three-dimensional brain housed inside a higher-dimensional black hole, with humans only existing as a single layer within a vast, multidimensional cosmos. Some string theories, such as M-theory, go so far as to suggest that black holes could serve as portals to other realms. If so, each black hole could be a distinct. In accordance with the laws of the universe, the bounce theory lends credence to the black hole universe concept. In this model, matter is compressed by a black hole, but rather than collapsing into an infinitely dense singularity, it bounces back, forming a new universe. This way of thinking suggests that black holes could function as a cosmic recycling process, constantly generating new universes from older ones. Of course, there are many obstacles to proving this hypothesis, as we cannot yet observe upper. Because of their enormous size and other extreme conditions, black holes are extremely difficult, if not impossible, to study directly. Experimental confirmation of this theory would necessitate technology that is currently unattainable, since the amount of energy required to model or observe a black hole's interior is greater than what we are able to produce. Opponents of the black hole universe theory counter that, from inside a black hole, we would perceive stronger gravitational effects, comparable to the intense gravity surrounding a black hole's. If our universe were a black hole, some say, we should see signals of an outer boundary, like an event horizon, but we don't. Others note that black holes usually have a singularity at their center, but ours seems to be isotropic or uniform, with no discernible center. This structural difference begs the question of how a black hole-like model could account for the enormous, even distribution of galaxies in our universe. Time in our universe flows at a relatively stable rate without the intense slowing effect expected near a black hole, according to cosmic measurements. Testing the black hole universe theory is difficult because of these limitations, but future technologies may help us find answers. For example, with the development of more sensitive gravitational wave detectors like those at LIGO, we may be able to detect signals that mimic the conditions inside black holes. With the help of AI-powered simulations and quantum computing, we may be able to model the interiors of black holes in greater depth, which could shed light on whether or not these conditions are compatible with the properties of our universe. If this theory is correct, it has far-reaching philosophical implications, including the possibility that our reality is just a projection from a hidden cosmic universe, and that other universes may exist within our own, with each black hole giving birth to a new reality. It's possible that our universe wasn't created in a single isolated event, but rather as part of a continuous cosmic process, with each new cosmos being born from a different black hole. This idea is related to simulation theory, which proposes that our perception of reality is actually only the surface layer of a much deeper structure within a black hole. As we delve into the intriguing realm of black hole universe theory, we can't help but wonder about the mysteries surrounding our cosmic origins. By studying cosmic backgrounds, observing black holes, and developing our technology, we may one day uncover clues as to whether our universe is actually contained within a cosmic black hole. As we continue to explore this possibility, it is imperative that we acknowledge the groundbreaking work of the pioneering scientists whose theories, experiments, and ideas have paved the way. John Archeel Wheeler, a physicist who coined the term black hole and investigated concepts like quantum foam, a theory where space-time fluctuates at the smallest scales, and the idea that reality arises from fundamental bits of information, a concept he called it from, introduced this concept to mainstream discussion and reshaped our understanding of black holes beyond gravitational sins to something far more complex with the potential to create entire universes. As a result of his work on the holographic principle, Leonard Susskind built on Wheeler's ideas and proposed that everything happening inside a black hole could be represented as a projection on its boundary, the event horizon. This idea not only changed our understanding of the cosmos, but it also altered our perception of the nature of information itself. Understanding of black holes, but also hinted that the entire cosmos could exist as a holographic projection within one in a higher dimensional space. Gerard H., a Dutch physicist who advanced the holographic principle, added fuel to the fire by suggesting that information within a black hole is preserved rather than lost, casting doubt on earlier assumptions and lending credence to the idea that the information of our universe could be stored on a boundary, similar to that of a black hole. Stephen Hawking's discovery of Hawking radiation, which demonstrated that black holes aren't static, isolated objects, and his work on black hole thermodynamics, which exposed a paradox about information loss, led to debates with Susskind and others about whether or not black holes destroy information, contributed substantially to these discussions, as did Hoof and Sussind's insights, which supported the theory that our universe could be encoded on a larger cosmic surface. In the field of theoretical physics, the preservation of information became an important question in determining whether black holes could generate new universes or serve as portals to other realities. Nikodem Pawlowski put forth the idea that black holes could generate new universes rather than singularities, grounded in Einstein's Cartan theory, which posits that black holes spin and induce a type of torsion that prevents infinite density, which could lead to a rebound. Pawlowski's theory that every black hole could potentially birth a new universe was in line with the black hole universe hypothesis, which provided a mathematical basis for how this process could work. Physicist Lee Moulin advanced these ideas further with his cosmological natural selection theory, which posits that black holes create new universes with slight variations in physical laws. Smolin proposed that the universe could function similarly to biological evolution, with black holes playing a role in the process. Roger Penrose presented an alternative view with his conformal cyclic cosmology, CCC, theory. According to Penrose, universes cycle endlessly, with each new universe beginning where the previous one ends. However, his theory does not explicitly support the black hole universe hypothesis. Instead, it aligns with the idea that black holes could be seeds for new realities, offering a unique perspective on how our universe might have emerged within a black hole. While Alan GDH didn't propose the black hole universe model specifically, his inflationary theory did demonstrate how space can expand tremendously in a short amount of time, similar to how a black hole's event horizon might expand as it consumes matter, which adds credence to the idea that black holes may play a role in the cyclical nature of universes, potentially resetting space and time to create new realities. Theoretical and experimental work have both contributed to the ongoing conversation about how the fast expansion of our universe could be a reflection of black hole dynamics. However, the most recent breakthrough in this area was the Event Horizon Telescope, EHT, which confirmed predictions from general relativity regarding the way light bends around black holes by imaging the supermassive black hole in galaxy M87. The LIGO Observatory's finding of gravitational waves, which are the result of black hole collisions and carry information about the properties of the colliding objects, lend credence to holographic theories that propose our universe may function in a similar fashion. With each detection, scientists learn more about the dynamics of black holes, which could help us understand whether such extreme environments could result in the creation of new universes. Hawking and Susskind's infamous disagreement over the black hole information paradox brought researchers one step closer to understanding whether black holes are more than just massive gravitational fields. Hawking had previously believed that information entering a black hole was lost forever, but Susskind argued that information is preserved on the event horizon. This debate ultimately led Hawking to reconsider his support for the idea that black holes may retain some information that could potentially impact the formation of new universes. Gerard H. Hoff and Leonard Susskind engaged in a significant debate regarding the nature of holography. While both men acknowledged that black holes store information on their boundaries, their approaches differed regarding the mechanics of this storage. Hoff's focus was on mathematical models, while Suskind's was on physical implications. Despite their differences, both men contributed to the development of the holographic model and its relevance to our universe, but have also impacted larger philosophical inquiries regarding reality. For example, the concept that our universe could exist within a black hole raises questions about the singularity of space and time and the possibility that ours is just one layer of a much deeper, multi-layered reality, with each black hole having the ability to birth a new universe. This line of thinking is related to simulation theory, which proposes that our universe could be a projection or hologram from a deeper reality, and that black holes could serve as boundaries where information is encoded. The Big Bang might not have been an isolated occurrence, but rather our universe could be a part of a cycle whereby each black hole creates a new cosmos with its own unique set of physical laws. This model of nested universes implies that black holes are the engines that propel the ongoing process of universe creation. If this is so, then our entire universe could be a cosmic simulation, with all physical events unfolding according to data encoded on a larger hidden surface. Scientists and the general public have been enthralled by the idea that our universe could exist within a black hole for a long time. However, recent advances in our understanding of black holes have shifted our perspective from viewing them as cosmic endpoints to seeing them as bridges to unexplored realities. This new way of thinking is shaped by a mix of experimental data, theoretical models, and philosophical insights. With the advancements in scientific knowledge and the development of more precise theoretical models, it appears as though the stars could align to form a cosmic structure in which black holes serve as portals to other dimensions. However, not all members of the scientific community share this enthusiasm, and there are many criticisms and challenges that cast doubt on the validity of the hypothesis. First, there's the problem with supporting this theory with evidence. So far, observations of stars, galaxies, and cosmic phenomena don't indicate that we're inside a larger black hole structure. Another problem is that there isn't an observable event horizon inside a black hole. This would be a major setback because the event horizon is the boundary where the gravitational pull is so strong that nothing, not even light, could escape. Since our universe doesn't appear to have an outer edge that acts as a gravitational barrier, we can't help but wonder if there's a black hole somewhere out there. Another problem is that the gravity within our universe isn't as strong as the intense gravitational effects that are expected near a black hole's event horizon. This would explain why time dilation and extreme slowing down are observed, but we don't see any cosmic structure that behaves like this boundary. Time in our universe flows relatively evenly, which begs the question of why it doesn't conform to the strong gravitational pull that a black hole would exert if we were inside one. What's more, our universe is isotropic, meaning that matter is distributed uniformly in all directions, which begs the question of why black holes, which are not known for such smoothness, would draw their contents toward their centers instead of keeping them evenly spread out. There is a noticeable disparity between the uniform distribution of matter in our universe and the chaotic interior of a black hole. One noticeable difference is the lack of a singularity, which is a point of infinite density inside a typical black hole. In contrast, our universe does not have a discernible center or focal point where all matter is drawn. Instead, it is vast and expanding with. The lack of a clear center makes it hard to explain how black holes work. And critics also point out that the expansion rate of our universe, which is being pushed along by dark energy, doesn't line up with the expected growth rate of an event horizon inside a black hole. If we were actually inside a black hole, we'd expect to see a different pattern of growth that reflects how black holes behave as they devour more mass. But instead, we see this acceleration. This seems to go against what one would expect from a black hole. After all, when we talk about dark energy, it complicates matters even further. Inside a black hole, gravity reigns supreme, drawing everything in toward its center. So, it's hard to understand how a force that actively pushes space apart could coexist with the idea that we're inside a black hole where gravity, not an attractive force, would dominate. Another reason to be skeptical is the presence of singularities. The Big Bang is thought of as a sudden expansion from a very dense and hot state, while black hole singularities compress matter inward, leading to an undefined point. This difference between the two events creates a gap in the theory. Hawking radiation also presents a problem, as black holes gradually lose mass as they emit this radiation. Our expanding universe doesn't show any signs of energy loss from its boundaries, which raises the possibility that we aren't inside a black hole. Another paradox is the apparent incompatibility between the size of our observable universe, which is vast and spans billions of light years, and the size of black holes, which is much more compact. This size paradox highlights a basic incongruity between the structure of black holes and the scale of our universe. From a theoretical perspective, general relativity has problems when applied to such large scales. While it does a good job of explaining gravity on cosmic scales, it doesn't imply that expanding universes could exist within the boundaries of black holes. Quantum mechanics also has problems because it doesn't naturally align with black holes. It is difficult to fully accept the entropy paradox and the idea of a universe within a larger black hole without empirical evidence. This is especially true when it comes to the preservation of quantum information across such a vast space, which is a key component of a universe model. Speculations about extra dimensions continue to plague the theory, as we lack the means to observe or interact with them. The entropy, a measure of disorder or information, is believed to increase over time within a black hole. However, our universe also has its own entropy, which grows as it expands. The question of how two entropic systems can coexist becomes complex when one is inside the other. Some critics go so far as to say that alternative inflationary theories provide a better explanation for our universe's expansion than a black hole model. Provided a well-grounded rationale for the early universe's explosive expansion, these models do not necessitate a black hole framework unless inflation is to be explained. Nonetheless, some regard the black hole as an extraneous complexity. Lastly, there's the matter of cosmic horizons within the black hole universe hypothesis. While cosmic horizons could be interpreted as the boundaries of a black hole, in reality, they're only the limits imposed by the speed of light and the age of the universe. These horizons need not indicate an external event horizon, but rather serve as a representation of the boundaries of what can be seen given the speed of light. From a philosophical standpoint, the concept of nested universes within black holes poses paradoxes. After all, if each black hole generates a universe, then an endless number of nested universes would form inside each other. This idea seems both untestable and endless, and the resulting philosophical questions further muddy the waters between fact and speculation, making the theory even more difficult to test. Additionally, numerous scientists have raised concerns about the theory's inability to provide testable predictions. According to falsifiability, theories should make predictions that can be tested and potentially disproved. However, the black hole universe hypothesis fails to offer clear ways to test or disprove this, leaving it as a largely speculative concept with limited room for empirical verification. These critiques serve to emphasize the hypothesis's complexity and shortcomings. Although the concept is intriguing, there are still many who doubt its practicality. Skeptics point to various factors, such as the laws of physics and mathematics, as potential explanations, such as dark energy and the effects of gravity and expansion, as well as the philosophical and existential concerns raised by the scientific community's criticisms of the black hole universe hypothesis. The holographic principle states that everything we perceive is an illusion of space and time created by the structure of a black hole. If our universe is contained within a black hole, it suggests that we are bound by limits that we cannot perceive or escape. This theory challenges the nature of reality and, in a way, reshapes our understanding of existence and our place in a much larger, possibly layered cosmos. What we perceive in our three-dimensional reality may in fact be a projection of data stored on a two-dimensional surface. This would imply that concepts like depth, distance, and time are not as fundamental as they seem, but rather the product of data encoded on a distant cosmic boundary. It's like watching a flat movie screen that somehow creates the illusion of three-dimensional space. It's possible that we are living in such a projection, a reality that is limited and defined by within the confines of the black hole that holds us, we are confined to what is known as the cosmic horizon. This limit prevents us from seeing or measuring anything beyond this point, much like our own physical and mental boundaries. Our minds have a hard time processing anything beyond what our senses can perceive or what our current understanding of the universe allows. May mirror the physical constraints placed by our assumed black hole's edge, suggesting that all we know is a part of a much bigger structure that we can't access in its entirety. Contemplating the cosmos within a black hole also changes our perception of existence. If each black hole creates a new universe, then ours could be just a bubble in a huge multiverse with innumerable other bubble universes existing inside black holes throughout higher dimensional space. This perspective would imply that life, the concept of existence and consciousness, could be seen as an emergent property that arises from encoded information. Our awareness, thoughts, and perceptions could be the product of this process, just as different forms of life could arise in different universes according to different physical laws. This would make our perception of our own specialness change, as our universe becomes just one small part of an endless cycle of creation. Complex information interactions at a cosmic boundary have led some to question whether consciousness is an independent entity or if the structure of the universe is predetermined by cosmic encoding. This has sparked philosophical debates regarding the existence of free will within these encoded limits, as well as the possibility of fundamental laws and behaviors being set by encoded information. Perceiving ourselves as part of a vast layered system, rather than the center of the universe, changes our perspective on scale and the nature of reality. Humanity has long held this view, but the concept of a black hole universe situates us within a cosmic hierarchy, suggesting that our universe is just one layer in a complex nested structure of realities. Inhabiting a black hole also raises the intriguing possibility of a universe that is a projection from some flat surface, giving rise to the idea of a simulation in which encoded information represents our reality. In the same way that a computer program can create an artificial environment that seems real to its users, our universe could be an intricate simulation built by the creators of. The perspective presented here casts doubt on the veracity of our perceptions, raising the possibility that they are just as artificial as the virtual worlds we can build with our technology. If our universe is actually a projection from a black hole, then what does this say about the nature of life and death? If our consciousness and physical existence are linked to data contained within a boundary, then maybe we are just transitioning between different states of. The idea that boundaries could encode all cosmic information suggests that life might transcend individual existence and become part of a vast network of information that continues beyond what we can currently observe or measure. The concept of interconnectedness grows stronger when we think about cosmic boundaries. If all information exists in this projected space, then consciousness may not end with physical death, but rather be part of an ongoing cycle. If the data about the cosmos is stored on this boundary, then everything in the universe might be linked in ways we don't yet understand. Human consciousness, in this framework, might not be an isolated experience, but rather a part of a greater universal consciousness that is linked across space through the encoded data on a cosmic boundary. If this is the case, then what is the purpose of human life? Is it purely coincidental, or does this cosmic structure have a greater purpose for our existence? The cosmic perspective reveals that individual lives are part of a larger system. Some may interpret this as a call to seek purpose in exploring and understanding this system and expanding human knowledge, while others may see it as a reason to focus inward. In any case, time becomes an intriguing concept when seen through this lens, and the projection of space and time makes it all the more intriguing. Maybe it's all an illusion, created by the encoding process on the boundary. Our perception of time moving forward could be a product of the universe's information structure. This makes us question if past, present, and future are just illusions within a greater timeless boundary. Thinking about consciousness in this way also brings up concepts of collective awareness, as if all beings in the universe are part of a single projected reality. It's possible that every individual's consciousness is just a small part of a greater, all-pervasive consciousness. If this is the case, then our limited awareness may prevent us from seeing some truths because our perceptions are clouded by the effects of the black hole within which we exist. On the other hand, maybe our consciousness is just the universe's way of reflecting on itself, a self-reflective quality that lets the universe become aware of itself through the conscious experiences of its inhabitants. Although this doesn't diminish the significance of knowing, it does bring attention to the limitless possibilities for discovery. As we push the boundaries of our understanding, we are aware that there may be more waiting to be found. Every idea reshapes our understanding of being alive, thinking, and existing. It challenges the line between reality and perception, pushing us to consider the possibilities beyond what we can currently measure or observe. The result is a vast and complex picture. Advancements in observational technology and theoretical models are paving the way for further explorations into these mysteries, as are compelling ideas about our place in the universe and the nature of self-existence. As we can see in the study of our possible existence inside a black hole, science has provided compelling insights. However, in order to put these theories to the test, we require tools that can observe and measure black holes like never before. Next Generation EHD, also known as NGT, is an important upgrade to existing event horizon telescopes that will allow us to see black hole event horizons with more clarity. This will help us learn more about the structure and behavior of black hole boundaries, which is crucial for understanding the nature of the event horizon that may define our universe. Other space observatories, such as the James Clerk Maxwell, will also contribute to this understanding. If our universe is indeed contained within a black hole, then studying these supermassive black holes could provide clues about how structures like ours could have come to be. The European Extremely Large Telescope, JWST, and the upcoming Lynx X-ray Observatory will allow us to peer into these black holes at the centers of faraway galaxies and study their formation and evolution in the early universe. The 30M telescope and the European Extremely Large Telescope will also concentrate on high-resolution imaging of black holes. The Laser Interferometer Space Antenna, also known as LISA, is a space-based detector that can pick up low-frequency gravitational waves. This observatory has the potential to detect waves from massive black hole mergers across great distances, allowing us to learn more about black hole interactions than what is currently possible with ground-based detectors. Other significant developments include gravitational wave observatories, such as in addition to directly observing black holes, we are also exploring quantum physics and high-energy experiments to learn about their inner workings. The Large Hadron Collider LHC, with its upcoming high-luminosity upgrade, may provide light on particle interactions at extremely high energies and the Einstein telescope and cosmic explorer will allow us to better map black hole events and observe cosmic scale mergers, potentially uncovering patterns that support the idea of a black hole universe. Energy scales that mimic black hole environments. For instance, some hypotheses propose that, under the extreme conditions generated by the LHC, micro black holes, or analogs of black hole events called horizons, could form. If this is true, we could study their properties directly and observe their black hole-like behaviors in the lab. Moving forward, experiments could be pushed even further by future particle accelerators like the Future Circular Collider (FCC) or a potential mu collider, which would allow scientists to explore interactions at even higher energies. Researchers are making great strides in comprehending the behavior of matter and gravity in the vicinity of black hole thresholds. By employing ultra-cold atoms and intense lasers, they have even succeeded in fabricating miniature black holes that mimic specific black hole characteristics. This miniature setup enables the study of phenomena such as quantum entanglement and Hawking radiation on a microscopic level. By developing increasingly advanced analog systems, we may gain fresh insights into the nature of black holes and the boundaries that may characterize our universe. Technology to study and recreate black holes is rapidly evolving, with artificial intelligence, AI, playing an increasingly important role. AI's capacity to sift through vast amounts of data has already shown promise in black hole imaging, where it processed data from the original Event Horizon Telescope to create the first picture of a black hole. AI-based simulations of black hole mergers, for instance, can now model these intricate processes in real time, illuminating the subtle. Machine learning, a branch of artificial intelligence, aids in the detection and analysis of gravitational wave signals. Despite the massive amounts of data generated by gravitational wave observatories, only a small percentage of this data actually contains useful information. AI is assisting in the process of filtering out this background noise, allowing us to identify signals from black hole mergers and other cosmic events, and perhaps even to uncover fainter signals that were previously undetected. AI has the potential to shed light on a perplexing paradox in theoretical physics, the black hole information paradox. This paradox concerns the preservation or permanent loss of information that falls into a black hole. By processing quantum information near black holes, researchers are training neural networks to estimate black hole properties, which is a previously overlooked area of study. AI has another interesting role in studying the cosmic microwave background, CMB, which is the leftover radiation from the Big Bang. Machine learning algorithms can detect faint patterns in the CMB, which could reveal connections to primordial black holes or early black hole formation. This could help us understand whether information is ultimately lost or encoded on the event horizon in cosmology. Discoveries that support the theory of the black hole universe are soon to be available, and researchers are hard at work creating new models to explain how a universe could form inside a black hole. With the help of singularity, high-performance computing, scientists can model intricate black hole environments and test various hypotheses, such as the role of higher dimensional spaces, the expansion of space-time within a black hole, and the role of string theory and loop quantum. There are two potential areas of research that could lead to new insights into black hole physics: string theory, which states that basic particles are one-dimensional strings, and loop quantum gravity, which aims to bring together general relativity and quantum mechanics by proposing a granular nature of space and time. If these theories are proven to be correct, they could shed light on black hole singularities and their possible role as portals to other dimensions. Despite the immense amount of theory and groundbreaking research on black holes, many fundamental questions about their nature and the universe's beginnings remain unsolved. Could a black hole actually contain our universe? If so, what does that imply for our perception of reality, existence, and everything beyond the limits of what we can see? The black hole universe hypothesis challenges our current understanding of the world and forces us to reevaluate everything we know, but with our current understanding of black holes is limited, and our lack of direct observation leaves us with many unanswered questions. For example, is the singularity of a black hole the end of the universe or the gateway to parallel universes. The possibility that black holes are cosmic seeds raises the intriguing possibility that the point we refer to as a singularity marks the beginning of a new realm. But until we can peer inside a black hole, this remains purely conjectural. Next, there's the hypothetical matter of information preservation inside black holes. According to Hawking's research on black hole radiation, black holes slowly evaporate, but what happens to the data that falls into them? If data really vanishes, our quantum mechanics knowledge would be lacking. On the other hand, if data is preserved, it would lend credence to the holographic principle, suggesting that everything within the black hole, including our universe, could be real. Dark matter appears to congregate around galaxies and interact with black holes, while dark energy propels the expansion of the universe. Could these phenomena be impacted by forces beyond our universe, connected to a larger cosmic structure, or are they leftover forces from black hole dynamics from beyond the event horizon? This last philosophical question remains unanswered. Think about it. What does it mean if we're actually in a black hole? Would it change how we see the universe, what our life's purpose is, and the importance we give to things? While existential questions have always troubled humanity, the idea that our solar system is part of a much larger cosmic system intensifies these thoughts. It implies that we could be a part of something much bigger, and what our current knowledge of black holes only scratches the surface of what the future holds. I hope you liked the video. If you did, please subscribe. I'll be adding more findings and maybe answers in the future.